I'd like to welcome today's speaker, who is James Zachos. Dr. Zachos is a professor of Earth and Planetary Sciences at the University of California at Santa Cruz. He received his Ph.D. in oceanography from this institution in 1988, and he followed that by being a postdoctoral fellow at the University of Michigan, for which I'll excuse him. I'm a Michigan State grad, but that's okay. Postdocs don't count in that regard. And he then was a fellow at the University of Cambridge. Dr. Zachos' research focuses on ocean, climate, and carbon cycle dynamics over geologic time, with a specific focus on periods of extreme warming. He reconstructs past ocean temperature and carbon chemistry by analysis of microfossils that were recovered from deep sea sediments. And you'll hear a lot more about that today. He has authored and co-authored 120 peer-reviewed publications on topics ranging from past greenhouse warming and ocean acidification to the onset of Antarctic glaciation. He is a fellow of the American Geophysical Union, the Geological Society of America, the California Academy of Sciences, and he's a recipient of the National Young Investigator Award, the American Geophysical Union Emiliani and Humboldt Awards. And not least, and last on this list, but probably not last, he is a member-elect of the American Academy of Arts and Sciences. And I'm pleased to welcome here today to tell you about ocean acidification in the past and what it means for the future. Yeah.
Okay, well, thank you for that introduction, and thank you for the invitation to speak here. I feel like this is my home. I spent many years here, and many memorable and very good years, and so it's always nice to come back and visit. Also, I'd like just to thank the Institute. I think the work that you're doing is critical and certainly very necessary. The presentation I have today will be about past global warming and ocean acidification, and there are benefits to looking back in time. One of the applications that we are all aware of is the evolution of the Earth's climate. We've spent a lot of time trying to learn about the Earth's climate in the past to understand more about climate sensitivity or climate dynamics. And the same could be said for the carbon cycle. We have theory about how the carbon cycle functions, the natural processes of, say, carbon sequestration, and we'd like to be able to test our theory by going back in time and looking for particular case studies that might be suitable for at least testing certain aspects of our theory concerning the carbon cycle dynamics. This particular figure just shows periods of extinction of calcifiers, and a number of these coincide with periods of extreme global warming and ocean acidification. And the one that I'm going to focus on today occurred about 55 million years ago at the Paleocene-Eocene boundary, a global warming event known as the PETM. And so I'm going to come back to this in a moment, but before I go there, I'd like to talk a little bit about what's happening now, just to get us warmed up, what's happening at least in terms of the current carbon cycle and what will happen in the future. This is just showing the emissions of carbon since 1800, and as you can see, there's been this rapid rise. Most of this has been through combustion of coal and oil and gas. We're starting to burn more and more gas of late. And what we know is that roughly 380 gigatons of carbon has been emitted to the atmosphere during this period, and about 150 gigatons of that carbon has accumulated in the atmosphere. Some of the carbon, as I'll show you, is being absorbed by the ocean, and we'll talk about the consequences of that in a second. The fossil fuel CO2 that's being released to the atmosphere comes from organic matter that was buried millions of years ago, and it has a very distinct carbon isotopic signature, basically the same carbon isotopic signature of the vegetation from which the fossil fuel came from. This delta C13 value of minus 25 is typical of plants, and that carries through to the CO2 that's emitted from burning fossil fuels. Now, the significance of that will be obvious in a second. This is just representing roughly the major reservoirs of carbon, the atmosphere, the surface ocean, the deep ocean. I threw the biosphere in there. And basically, we're upsetting the balance of this carbon budget with a fossil fuel combustion. And this 5,000 gigatons is actually quite ancient, as I'll show you in a moment. But that's the estimated fossil fuel reserves, say, about 10 years ago. And we've been adding carbon, and as I said, roughly 150 gigatons of carbon have accumulated in the atmosphere. And some of that carbon has accumulated in the surface ocean. Now, the carbon isotopic fingerprint that I mentioned earlier about the fossil fuel fingerprint, delta C13, for those of you who are not familiar with carbon isotope notation, it's simply reflecting the ratio of two stable isotopes of carbon, C13 to C12, relative to a universal standard. And the standard typically has a ratio very similar to the carbon that's already in the ocean. And so we're effectively adding carbon that has a value of about minus 25 per mil into this larger reservoir of carbon that on average has a delta C13 ratio of about 1 per mil. So this is significantly lower ratio of C13 to C12 compared to the carbon pool that it's being added to. So is there a signature, a clear signature of this carbon accumulating in the atmosphere and the ocean? And the answer to that is yes. And this particular diagram will illustrate how well we can actually track the movement of fossil fuel from reservoirs into the atmosphere and ocean. The first curve that I'm showing here is simply 1 over the concentration of CO2, starting from 1350. And what I'd like to point out here simply, this is where the rise of CO2 begins. What we know about atmospheric CO2 over this time period depends largely on archives, geologic archives. And most of you know that beyond the period of modern measurements, what we know about atmospheric CO2, we know from ice cores, by sampling bubbles in ice cores going back through time. And that gives us samples of the ancient atmosphere. And so that's how we know most of this trend in CO2. Now, the nice thing is once you have that CO2, you can actually measure the ratio of C13 to C12 in that CO2. And people have done that. And this next curve is just showing the variations in the C13 to C12 ratio of that CO2 from the bubbles in the ice cores. And so that's the atmospheric composition rapidly starting to decline, the ratio declining as fossil fuels are being added to the atmosphere. And then for the ocean, we would expect, at least in the upper ocean, the ratio of C13 to C12 to change almost as rapidly. The exchange of carbon between the atmosphere and the surface ocean is very rapid, and so they're almost in equilibrium. And how would we measure the ratio of C13 to C12 of carbon going back through time beyond modern observations? By sampling corals. Corals are recording the C13 to C12 of dissolved carbon of seawater near the surface of the ocean. And this was done by Baum et al. In 2002, and they show how the ratio of C13 to C12 of corals has declined over this period. And so the changes in the C13 to C12 of the atmosphere and the ocean are, in fact, a fingerprint of the addition of anthropogenic carbon to the ocean. You can use these numbers to even estimate roughly how much anthropogenic carbon has accumulated, and you'll come up with something like 100 gigatons of carbon for the surface ocean. And so that's close to what observations suggest. Now, of course, the absorption of carbon by the ocean, CO2, is what we're focused on today. And the problem, of course, is that the addition of CO2 produces carbonic acid, a weak acid, and so this lowers the pH of seawater. And I had Ken Caldera, he was visiting Santa Cruz a couple of weeks ago, and he gave me a couple of slides that illustrate the acidification process, and so I'm just going to run through these. So this is representing seawater with a water molecule here and a bicarbonate molecule here and a carbonate molecule here. And this is the main buffering capacity of the surface ocean. The addition of CO2 involves a hydration reaction to produce carbonic acid. And then this dissociates, and you have free hydrogen ion, which ultimately will react with a carbonate ion. And so there's a loss of a carbonate ion for the addition of one bicarbonate ion. And then ultimately, to balance the loss of the carbonate ion, calcium carbonate from sediments could dissolve, releasing additional carbonate ion into seawater. Okay, so that's the reaction. This reflects the changes in the relative abundances of carbonate ion, bicarbonate ion, and CO2 as a function of pH in seawater. And so what I was representing was simply this lowering of pH, which effectively is taking up carbonate ion and producing bicarbonate ion. Now, it's the loss of the carbonate ion, the reduction in carbonate ion, that's a problem for marine calcifiers. And so if you look at this in sort of the time domain moving forward, this figure shows 3 parameters. The lower curve is the partial pressure of CO2. Here's the rise into the future toward 2100. And then what you're seeing in the other 2 parameters are pH, the response, the drop of pH, and then the corresponding drop in the carbonate ion concentration of seawater. So this drop in carbonate ion concentration is actually quite significant. When you look at the scale here, it's definitely much larger than you would likely believe seawater could actually change. Now, here's the issue for calcifying organisms. The saturation state of seawater for carbonate or calcium carbonate is set by the concentrations of calcium and carbonate ion. And so if the concentrations of those ions drops too far, the saturation state could get to a critical level where seawater is actually undersaturated with respect to calcium carbonate. We have this term omega that represents the saturation state, and omega is simply the observed product of the concentrations of calcium and carbonate ion relative to what would be needed to maintain saturation. And for this calculation, we typically ignore the calcium concentration because it's relatively high, it's not dropping. And so you just have to simply look at the observed carbonate concentration relative to the saturation carbonate concentration. And so for omega, what we concern ourselves with any values that are below 1, that would represent an undersaturated situation. Values over 1 represent an oversaturated water or seawater sample. So looking at the distribution of carbonate ion in today's ocean relative to saturation, this figure shows the relative saturation levels for maintaining omega-1 for both calcite and aragonite. And calcite and aragonite are 2 polymorphs of calcium carbonate. Aragonite is a little less stable than calcite, so it requires a slightly higher carbonate ion concentration to maintain omega greater than 1. And then you have the observation of actual observations of carbonate ion concentration as a function of depth. This is from the South Atlantic. And you can see for most of the ocean, the carbonate ion concentration is relatively high, well above the level to maintain omega greater than 1, until you get to a certain depth for both aragonite and calcite, and then the ocean becomes undersaturated. So if you calculate omega just based on those carbonate ion concentrations, these are the profiles for omega in the Atlantic and Pacific Ocean basins. This is for calcite. And then for aragonite, omega is slightly lower for the same carbonate ion concentrations. Okay, so omega is changing. That's starting to decrease with the decrease in carbonate ion concentration. If you look at the change in surface ocean pH over the last 100 years, we're already seeing fairly large changes in reductions in pH in places like the North Atlantic and in the Southern Ocean. Okay, so this is the invasion of anthropogenic CO2, the lowering of pH. And of course, if the pH is dropping, we would expect the carbonate ion concentration to drop. And so that's what this figure shows, is the reductions in carbonate ion concentration during the same period. And this is quite large. It's actually quite impressive how much the carbonate ion concentrations have declined. Now, there are projections out into the future, and I'm going to show you one. This is based on a model that I'll talk about a little bit later. We've been applying the same model to look at past ocean acidification events. But basically, this is the changes in omega as a function of depth and time moving forward from 1750 to 2750 in the first panel, and then long-term out toward 12,750. And so you can see the changes in the saturation state of the ocean, the reduction near the surface ocean, and then eventually the saturation state slowly starts to recover. Now, just very quickly, omega, at least as far as corals are concerned, there have been all sorts of studies conducted growing corals in laboratory settings at different pHs, different saturation levels, to try to gauge what their sensitivity is to varying levels of pH. And it's clear that as you get to lower and lower saturation levels, and these are corresponding levels in atmospheric PCO2, that the calcification process becomes more difficult, more challenging. There are organisms that can still calcify. It just takes a lot more effort to do that. And so as we go forward in the future, again, Ken Galdera provided me with these slides. This is just showing the saturation state. And you can think of it as time moving forward of the surface ocean responding to the rising levels of atmospheric CO2, 380 ppm, 450 ppm, 550, 750 ppm. And at 750 ppm, we'll probably be there before the end of the century, certainly at current rates. I don't think there's any doubt about that. And so really it's just a question of how high we might go. And for years and years, when we talked about fossil fuel emissions and ocean acidification and global warming, the number we kept talking about was 5,000 gigatons of extractable fossil fuel. And of late, that number has started to change dramatically. And people are starting to throw around numbers like 10,000 gigatons of carbon, thanks to fracking and deep water drilling. And so these numbers obviously depend on a lot of factors, economics, all sorts of other issues. But nevertheless, we can start to think about, say, a 5,000 gigaton emission scenario. So if we start to look even further out into the future, and we did go ahead and say, put 5,000 gigatons of carbon into the atmosphere ocean, say over several centuries, this is effectively a model simulation of what that would look like in terms of PCO2. We'd see this abrupt rise in PCO2 and then this, at least recovery, this following sort of exponential decay trend. This is the change in surface ocean pH, the dramatic drop in pH. This is the change in omega. It gets down to 2, between 1 and 2, but doesn't quite get below 1, at least in the surface ocean. And then we also have carbon isotopes. I threw that in this particular simulation. we assume the carbon has a delta C13 of minus 25. And what you are seeing is a dramatic change in the ratio of C13 to C12 in the ocean. And it's actually amplified in the surface ocean because initially most of that anthropogenic carbon is accumulating just in the upper layer of the ocean. The ocean's stratified, and the mixing of ocean actually takes hundreds of years, millennia, to completely overturn. And so because the rate of emission is so fast relative to the overturning of the ocean, that pH effect, that acidification effect is effectively concentrated in the upper 300 or 400 meters of the ocean. And this is a rate issue. Now, the one striking thing about this is that over the time that this model simulation is run, 100,000 years, the CO2 levels and the pH and the carbonate chemistry of the ocean has not returned to pre-anthropogenic levels. And this is something that theoreticians have seen in the models for many years. And what it reflects is the slow sequestration or removal of carbon from the ocean atmosphere system, primarily through rock weathering. It's a very slow process. And so this is something that is sort of striking, and it's worth thinking about, that the longevity of this fossil fuel perturbation will be long-lasting. Now, are there past analogs for assessing or testing this theory? And of course, the answer to that is they're not exact analogs, but there are certainly events that have occurred that are very similar in character to what happened or what's happening today and what will happen in the future. And so I'm going to take you back in time, 55 million years, to the boundary between the Paleocene and Eocene epochs. And this was an interesting time. We have a number of interesting changes that have occurred at the boundary. Primarily, first and foremost, is a global warming event. Transient in nature, about 5 to 6 degrees of warming. The warming was relatively uniform over latitude, which is actually consistent with greenhouse forcing in the absence of ice albedo feedbacks. We also have evidence for intensification of the global hydrologic cycle, which in itself is a really important story. There's evidence for a reduction in the rate of overturning of the ocean, and this is consistent with warming of the high latitudes, and the manifestation of this is a reduction in dissolved oxygen levels in the ocean. And then there's evidence for disruption of both marine and terrestrial ecosystems. And part of that includes just changes in species abundances, the latitudinal gradients of various species shift toward higher latitudes. There's some extinction. We would say minor extinction, at least on a relative scale of the geologic past. Now, much of what we know about the changes in climate and ocean chemistry are coming from our deep sea sediment archives, and one of the main tools we have for recovering those archives is the JOIDES resolution, which can core virtually any place in the ocean to depths of a few thousand meters below the seafloor. And so the layers of sediment are effectively like pages in a book, and as we go back or deeper into the sediments, we move further back in time. And then for some of us, the information that we use to reconstruct aspects of the past ocean climate, our temperatures and chemistry, we extract that information from the shells, the calcareous shells of the creatures, the marine organisms that inhabited those oceans. And this includes both planktonic calcifiers like foraminifera, planktonic foraminifera, and also benthic organisms like the benthic foraminifera. And so we can measure the shell chemistry. For instance, we can measure the ratio of O18 to O16 in the shell. And the partitioning of O18 to O16 from seawater into shells is actually highly temperature dependent. And so by calibrating the O18, O16 ratios of shells grown in the laboratory at different temperatures, we can come up with a calibration curve which we can then apply to fossil shells to reconstruct the temperature of the water in which they grew. And so for much of the last 100 million years, what we know about the temperature or the thermal evolutions of the oceans, we've determined by using this oxygen isotope technique. Now what I'm going to show you are several records that were generated back in the late 1990s across the Paleocene-Eocene boundary from cores taken in the Atlantic, Pacific, and Southern Oceans. And these are measurements of the oxygen isotopic composition of foraminifera, moving forward in time this way, in this direction. And so starting in the late Paleocene, the temperatures show this sharp, dramatic rise of about 5 to 6 degrees centigrade. And we record this uniformly throughout the deep ocean as well as in the surface ocean. There's some amplification in some regions, as I'll show you in a second. This is just a reconstruction of the peak sea surface temperatures during the Paleocene thermal maximum. And below that is just the change, the anomaly, the rise in temperature at each of those locations. So as I said, the warming is relatively uniform over latitude, 5 degrees at the pole, 8 degrees in the Antarctic. But the peak temperatures are quite high, and you can see 22 degrees in the Arctic, 20 degrees off of Antarctica. The tropics got fairly hot. There aren't many records from the equatorial regions. This is one data point from near Tanzania, but 37, 38 degrees there. And just to give you some sense of what the planet might have looked like, I borrowed this from this National Geographic article, and this is produced by Ira Block, and it's the Arctic today, and then a native holding a photograph of what the Arctic would have looked like at the peak of the PETM. Clearly a bit warmer and a bit greener than what's there today. If you go to places like the Bighorn Basin in Wyoming, we've done a lot of work in these continental sections as well, and the PETM has a very distinct character to it. We know a lot about the vegetation before the onset of the event. It actually got drier and hotter in places like Wyoming during the peak of the event, and so a whole nother interesting story could tell about those changes. So we have this evidence of the warming, and there's this other record here that comes when you measure the oxygen isotopes in these shells. You also measure the ratio of carbon isotopes, C13 to C12. And what's interesting is at the time of the warming, there's this decrease in the ratio of C13 to C12, and it's quite large. It's 3 per mil. It's hard to actually change the isotopic composition of the entire ocean by 3 per mil. And the only way you can do it is by adding a lot of carbon that's isotopically depleted, like fossil fuel carbon, minus 25 or minus 30. When we saw this, we knew that had to be a major carbon cycle perturbation. And so the input of thousands of gigatons of C12 enriched carbon was sort of a really critical moment. We realized that this was in fact a major greenhouse event. Right away we started thinking about where did it all come from? Where do you get thousands of gigatons of carbon from? And so the first thing we felt we needed to do was constrain the mass. We need to know how much carbon was released. As it turns out, that's not an easy thing to do with the carbon isotopes, because there are multiple sources of carbon with various carbon isotopic signatures. But what we did have was this. This is the calcium carbonate content of sediments from a series of cores just in one location in the South Atlantic. And typically the calcium carbonate content of the deep sea sediments is relatively high, something on the order of 90% or greater. And then as you can see in this diagram, when we have the warming and the carbon isotope excursion, the calcium carbonate content of the sediments in the South Atlantic goes to 0. It just goes away. And this would be very consistent with the notion of adding a lot of CO2 to the ocean atmosphere system. You would acidify the ocean, and in response there would be a buffering reaction involving the dissolution of carbonate on the seafloor. And the nice thing about that is if you can constrain the degree of dissolution of carbonate, the changes in the ocean carbonate chemistry, you can quantify the mass of carbon that was added to the ocean. And so once we had this, we realized we had an opportunity to actually determine how much carbon was released. Was it 1,000 gigatons, 4,000, 10,000 gigatons? So the way this works has to do with the way the ocean buffers itself. We have this zone of oversaturated waters, and as you get deeper into the ocean, when the carbonate ion concentration crosses the saturation horizons for either calcite, well, mainly for calcite, below that depth the ocean is undersaturated and you have no preservation of calcium carbonate. This is called the calcite or the carbonate compensation depth. All right, and you can see that the compensation depth could change simply by changing the carbonate ion concentration. Lowering the carbonate ion concentration by adding lots of CO2 would cause this intersection point to effectively shoal. Okay. And if you lower the carbonate ion concentration enough, you could actually get the compensation depth to shoal to less than 1,000 meters, which would be something. And it's probably going to happen in the future, by the way. And then with time, the carbonate ion concentration will recover as CO2 is slowly removed from the system. And so the carbonate ion concentration will recover, and then the CCD will restore. Probably not to its original position. It might actually overshoot its original position. So the strategy that we embarked on for at least constraining the mass of carbon release was quite simple. We were going to use output from different classes of carbon cycle models, from simple box models to complex Earth system models, 3D Earth system models. And we were going to run a series of experiments with different inputs of carbon, 1,000, 2,000, 3,000, 4,000 gigatons, and then use the observational constraints from the shifting position of the CCD, as well as the carbon isotopes, to constrain the models effectively to test, find the best fit with the simulations. And so the trick with reconstructing the CCD depth is that you need to drill a series of cores as a function of depth along some sort of submarine high, a volcanic pedestal, and recover sediments that span the Paleocene-Eocene boundary at depths of, say, 4 kilometers, 3, 2, and 1. And in doing that, you would be able to reconstruct the position of the CCD. And we did this, we had cruises going out to the Pacific, the Shatsky Rise, also to the Walvis Ridge here in the South Atlantic. This cruise was in 2003, and so this is just the rig floor of the Resolution, and this is me looking through the liner of one of the cores that had been brought up, just to see if I can see within the white mud a dark band. And the places that we drilled, at least on the Walvis Ridge, started at the top of the ridge and then moved down to the basin floor. This is just a seismic profile showing the layering of sediments below sea surface, or the seafloor surface. And then I'm going to show you the cores that we bring up. We split these cores, and as I said, typical mud on the seafloor, and this is mud. This stuff is 55 million years old, but it still feels like mud. Very fine-grained, very carbonate rich. And what you can see here is this clay layer. This is the PETM. This is the boundary between the Paleocene and the Eocene. And this was pretty exciting when this came up. It was the first site that we drilled. It was the deepest in terms of water depth. It's enough to get you your photograph in the National Geographic. Although from this you get the impression that I swam out there, put a core down, pulled it out, and swam back. It made my mother quite happy, which is all I care about. So, we started at the deepest site, then we went to the top of the rise, and then drilled a series of sites coming back down. And at all of these sites, we recovered this clay layer. This just shows the distribution of sites from the shallowest, the top of the ridge, to the deepest. The difference in depth is from 2.7 to 4.8 kilometers. And this is the calcium carbonate content in each of those. And you can see how the calcium carbonate content drops to 0 in the clay layer. And we see this at all the sites. And what's interesting is that the thickness of this clay layer is greatest at the deepest site. So as you would expect, the CCD rapidly shoaled over 2 kilometers and then gradually recovered. All right. And the question is, how long did it take to recover? And we were able to work that out after the Cruz building stratigraphic models. And so what you're looking at here is absolute time on this axis, and this is just relative time in hundreds of thousands of years from the onset of the carbon isotope excursion shown here. And this is just the calcium carbonate content of those 5 cores now plotted versus time. And so what you see is the carbonate content dropping, again, abruptly at all 5 sites, and then gradually, one by one, it comes back to each site. The carbonate deposition is restored at each site as the CCD is recovering. And this whole episode of onset to recovery takes just about 100,000 years. Okay, so it's consistent with theory. Right away, we knew that we had evidence that would support theory of what we currently understand about how the carbon cycle, how carbon is sequestered through natural processes. Okay. As I said, we had a number of models that we were using. I'm just showing output from one of these. This is the Genie Earth System model based in the UK. Andy Ridgewell is one of the architects of this model. It's a 3D ocean atmosphere model. It includes full biogeochemistry, tracks carbon, nutrients, and so forth. It has biology, net primary production. And so you can use this model to simulate, for instance, the distribution of calcium carbonate on the seafloor, basically the position of the CCD. And this is just output from the model showing where the CCD would be today, and this pretty much matches what we know about the distribution of calcium carbonate on the seafloor. And then here's examples of simulations with 9,000 gigatons or 4,500 gigatons with sediment bioturbation on or sediment bioturbation off. And what it does is it produces profiles of calcium carbonate deposition on the seafloor. It does it in a way that we can compare to the actual observations. And so after a number of these sort of experiments, Andy came up with a number of something like 6,800 gigatons of carbon. And so he's run additional simulations with this, just showing how the saturation state of the ocean would evolve. This is over an 11,000 year period with 6,800 gigatons. And you could see how omega decreases and decreases. It's a slow release. It's over 10,000 years, okay? It's not an abrupt release. It's a slow release. And so at the point you stop releasing that, then you start to see a recovery. But most of the ocean below about 500 meters is undersaturated with respect to calcite, and that's consistent with observations that we have. Okay. We've done this with other models, and we're coming up with numbers that are in that sort of 4,000 to 6,000, 7,000 gigaton range. And you can debate about which models are best for trying to get at this number. And what I wanted to end with was simply showing you some sensitivity tests that we were doing. This is work I've done with Richard Zabi at the University of Hawaii. And we did an initial experiment where we just released 2,200 gigatons of carbon and over a period of about 4,000 years, which is our constraints on the onset. The rate of release are not as good as we would like. We're kind of limited by the tools that we have for determining time in the past, but we can run these sorts of simulations. And so if you release 2,200 gigatons over 2,000 years, this is how omega of the surface ocean responds to that, okay? And we're out there looking for evidence of that now, for that kind of response. And we actually have some new data. I can't show it to you. I just don't have enough time. But it involves boron, boron isotopes. This is the anthropogenic signal, right? And the point here is the time involved, okay? If it's 5,000 gigatons, it's going to be released in a window like that relative to what we saw at the PETM. And that will be the impact on omega, on the saturation state of the surface ocean. Again, it's just this relatively fast rate of release relative to the mixing time of the ocean that causes this really sharp response in the saturation state of the ocean. We published a paper back in 2008 in Science. We intended this for policymakers, basically just showing options for emission scenarios in terms of the mass of carbon that we're going to release and the time scale for release, 500 years, 280 years, and what impact this would have on CO2, but more importantly, from the perspective of ocean saturation state, the impact it would have on the surface pH. And so again, you can kind of see how with these different emission scenarios, the pH will drop, and anything probably greater than 0.4 would be bad, really bad. And so this is sort of something to think about. You know, is there anything we can do to slow the rate of fossil fuel emissions? Okay, so how am I doing on time? Is that good? Okay. Here's my summary. At this point, we've I think as a community, we've settled on the notion that 4,500 gigatons of carbon was released during this event. And it kind of scales with the magnitude of warming that we see as well, and what we know about climate sensitivity to changes in greenhouse gas level. It's a large number, and I could spend a lot of time talking about where it came from, because we're still trying to figure that out, where all this carbon came from. And that's something I'd be happy to answer if you want to know that. But clearly we have the evidence of acidification. The entire ocean became undersaturated at depths below 500 to 1,000 meters. The full recovery by weathering feedbacks took over 150,000 years, and that's very consistent with theory. And as I said, what we're doing today in terms of the pH response will be much more severe than what we saw at the PETM. That would be a best case scenario. But like I said, this rate is just an order of magnitude faster than what we see. And so clearly this is something to be worried about. It will have impacts on marine calcifiers. Corals will probably, as we know, will be gone by the end of the century. And I say that, I'm not an expert on corals, but just from my perspective, that's what I would bet on. And so I'll leave it at that. Thank you.